The last section in Chapter 7 is about exponential growth and decay. So this is where we'll start getting into some word problems and solving and writing our own exponential functions. So an exponential growth means for a graph that it's going to be going upwards and increasing up. It also means that my initial amount will be greater than 0 and my growth factor, the b, will be greater than 1. So in this format, remember my initial amount is this a value, and that my base or my growth factor is going to be something bigger than 1 if it's going to be exponential growth. Now, in order for you to write out your equations, you're going to want to use this model where you're going to have an initial amount, which you can use whatever letter. But for your rate, for that growth rate, you're going to have to add 1 to that percent before you plug it in. So let's take a look at an example. In this problem it says, since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. In 2005, about $360 billion was spent at restaurants. If the trend continues, about how much will be spent at restaurants in 2015? So if I'm going to be setting it up in this form, my initial amount would be where I started at. So I'm starting at 360 billion. Now we're just going to write it as 360, and then in our answer we'll write billion dollars. For the R, I'm going to change this percent into a decimal. So remember, to change it into a decimal, it's currently behind there as a percent, so then I move it over 2 spots to the left and add in any zeros to fill in the gaps. So that's why my percent changed to a decimal form is 0.07. And then my time, I'm having to go from 2015 to the year 2005. So I'm going to have to subtract those two in order to find out what my time is, which is why I'm going to use 10. So after I figured out what my 3 variables are, I'm going to plug them into my equation. So 360 was my initial amount. I'm going to add in the 0.07. Now notice I'm increasing, so that's how I know I'm going to be adding in a positive. And then over here my time is 10. So then I just type this into my calculator exactly like it says. So I would type in 360 parenthesis 1 plus 0.07, close the parenthesis, and raise it to the 10th power. Then you should be getting about this number, so 708.17, and then I would add on the dollar sign, and I would also add on the billions word because I'm talking about in terms of $1 billion. Okay, you're going to pause the video and see if you can set up the got it question. So in the got it question, I was underlining some of my important information. So my initial amount is starting at 285, and then my rate is increasing, so I'm going to be adding in a positive, and I change my percent to a decimal, so 0.75. And then for my time, I have 2 years, so I want to subtract and find the difference between the two. So I would subtract them and I would get 9 years. So then plugging in, I would have 285, then in parentheses 1 plus 0.75, close the parenthesis, raised to the tenth power, which I put in as 9. When I type that into my calculator, I get around 43,872 because I rounded it to the nearest whole number, and then I would add in my label, which is subscribers. Okay, so those 2 problems only dealt with exponential growth. Another kind of problem that works exponentially is when you talk about interest. So remember, when you have a savings account, your account earns interest for just having money inside of that account. So some accounts have compound interest, and in order to calculate it, you can use this formula. So it's very similar to just the exponential growth, but they've changed out the P and put in the changed out the C and put in the letter P. So you still have the initial amount, you have your rate, and then T is still in terms of years. So let's look at an example. You have $6,500 invested at 2.5% interest compounded annually. If you start in 2014 and stop in 2027, how much money would you have? So setting up just like we would before, my initial amount would be $6,500. I'm going to change my rate into a decimal form. So I am moving this current decimal over 2 spots. So that's why it's going to get changed to 0.025. And then for my years, I need to subtract these 2 years, so I end up getting 13. Excuse me. So then I'm going to plug in my values. 6,500 parentheses 1 plus 0.025, close the parentheses, raised to the 13th. Type that into my calculator. I get roughly $8,960.32. Now I rounded to the nearest cent, so that means I was looking at this number behind here to tell me if I needed to round up or down for that too. Okay, the other kind of exponential is if it's decaying, which means that it would be decreasing. So first off, from the graph, I know it's exponential decay if it's pointing downwards or decreasing from left to right. If I'm looking at it in terms of a function, my initial amount still is any number, and b has to be less than 1 in order for it to be an exponential decay. So this right here would be what you may want to highlight, just so that you remember that my growth or my decay factor has to be less than 1 in order for it to be decaying. Okay, so let's look at some problems. Down here you are asked to find growth factors, initial amounts, decay factors. So it says, what's the growth factor in the equation? Well, my growth or decay factor is always the b value, so my answer is just 4. What's the initial amount? Well, when I'm talking about initial amount, it's always the first number that I have there, which is why it's 15. And then in the decay factor, my decay factor is always the b value, or the second number, which is why it's 0.2. Notice for the decay factor, I'm less than 1. Notice for the growth factor, I'm bigger than 1. That's how I know if it's exponential growth or exponential decay. Okay, last problems here, and it's word problems dealing with decay. So you can use this format, but the biggest thing is knowing from the word problem if you are decaying or if you're growing, and you'll always have key words in there. So let's read through example 3. It's talking about in physics, the kilopascal is a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. For every 1,000 meters increase in altitude, the pressure decreases about 11.5%. What's the approximate pressure at an altitude of 3,000 meters? Okay, so remember, the first number is my initial amount. So where am I starting at? Well, I'm starting at 101 kilopascals. So I would say that C would be at 101. Then my rate, I am decreasing by this amount. So that's how I know I'm going to be using decay, because it's going to be decreasing or a negative value. And I need to change this into decimal form. So even though it's a decimal, it's also a percent. So you need to change it into its decimal form by moving this decimal over 2 spots to the left. So it would be 0.115. And then last, for my time, or my exponential. In this case, t is going to be represented by your altitude, and it's saying for every 1,000 that it increases. So I already did 3,000 meters, so I would need to divide to see how many 1,000s are in there. So that's pretty simple. There are 3 1,000s and 3,000. So that's why I'm going to use 3 as my exponential for t. So setting that into my equation, my initial amount, putting in my 1 minus this. So it's decaying because it's decreasing, so that's why I'm doing minus, and then put in my exponent. Put that into my calculator, I end up getting this number, and then I add on my label at the end. Okay, you're going to pause the video and try the last question. Okay, on the last one there, you have an ant farm. So the first thing is pulling out your important information. So I had my initial amount, which was 3,137 ants. Then I had my rate, which is 0.22, and then my time, or my exponential, it's wanting to know after 2 weeks. But notice here it says it's decreasing per day. So changing that wording so that it matches, so 2 weeks is going to change into 14 days. So that's why I'm plugging in 14 for my exponent. So I put in my initial amount. I do 1 minus this since it says disappearing. I know it's getting smaller. And then I put in my exponent, which we changed to match the same wording. So I changed from weeks to days, and then put it in my calculator. Now here is one thing to note. If I'm dealing with ants, I'm obviously not going to have 0.8 of an ant. So you want to make sure that you end up rounding that to whole numbers and then put on your label. So that goes for any kind of story problem. Make sure you pay attention to what the object is in the problem so that you can round accordingly. So if you're talking about money, it's okay to round to a decimal point. But if you're talking about certain objects like books, ants, animals, make sure you round to the nearest whole number. Okay, exponential growth, exponential decay. Exponential growth is going to be increasing as a graph left to right. I also know that in my wording that it's going to be talking about increasing, it's going to be talking about going up, so that's how I know I'm growing. If I'm doing exponential decay, my graph is going to decrease from left to right. And then also in my story problems, I'm going to look for words that show that it's going down, so disappearing, decreasing, declining, something like that.